Hello, and welcome to this video on parallel computing. I'm here to provide you with valuable insights. The voice you're hearing is AI generated, and this video is supported by the Norwegian Research Infrastructure Service. NRES is collaboration between Sigma 2 and the universities of Bergen, Oslo, Tromsø, and NTNU to provide national supercomputing and data storage services. These services are operated by NRIS and coordinated and managed by Sigma 2. In this video, we will provide more details on executing jobs on Betzy. In our earlier videos, we focused on performance testing various parallel computing techniques for matrix multiplication using a Fortran program. During these tests, we employed some Python testing scripts. After completing the testing phase, you'll schedule your computation code as a production job. We'll provide some recommendations on how to organize a job script for this purpose, but keep in mind that these are simply suggestions. Once logged into Betzy, you'll see that I've been directed to the Login To node. Let's move to the OpenMP on Betzy directory that I have created within the work folder by using the cd command. We can display the contents of this directory by using the ll command. You've previously seen the Fortran program that utilizes OpenMP, but let's review it again. We note that the program uses a matrix dimension of 32,768. The matrices are initialized with values using an initialization loop, where the OpenMP directives can be observed. The matrix multiplication is executed through a triple-nested loop, and once again, take note of the OpenMP directives. We've named the job script to correspond with the Fortran program, with the distinction that the script has an SH extension while the Fortran program has an F90 extension. This naming choice indicates that the job script is meant to execute the Fortran program. However, this is just a suggestion, and you are free to use any naming convention you prefer. Let's review this job script using the Emacs editor. The job script starts by setting names for the job and the Slurm output file. Next, we define the computational resources needed for the job. We request a single node with a single task because the Fortran program employs a pure multi-threading approach with shared memory for parallel computing using OpenMP. The Betzy Linux cluster provides 128 CPU cores per node, and we request to utilize all cores for our task. We set the wall time to 30 minutes, allowing us to queue in the development queue. For a production job, a longer wall time is usually necessary, requiring us to wait in the regular queue. In this case, we must remove the Quality of Service (QoS) option. Regardless of the queue, providing the account number is mandatory. The script variable file holds the name for both the script and the Fortran program, and this variable is applied later in the script. The suggested error handling environment is implemented. We also need to load the Intel Fortran compiler. It's important to note that we are not using the Intel alias defined in the bash rc file, which we use to load the Intel Fortran compiler from the command prompt. This is to ensure that our job script does not rely on any specific configurations from the bash rc file in the home directory. The Fortran program utilizes OpenMP for parallel computing, so we are configuring some OpenMP variables. You might remember that during performance testing, we specified these variables directly in the execution command. However, here we are setting them as environment variables. The number of threads is configured to match the number of CPU cores per task by using a Slurm variable that retrieves this number from the computational resources defined in the script. Additionally, we employ the OpenMP affinity settings, CORS, and close. The script compiles the Fortran program to ensure it is built on the same type of compute nodes where it will do parallel computing. We need to replace the Broadwell architecture specification with the X-host option. The Intel compiler is used along with the script variable file, which contains the name of the Fortran program. The executable generated from the compilation process is named mxm.exe. We've included script variables to calculate the compilation duration, and this time is recorded in the Slurm output file. This measurement is optional, so you can decide whether to incorporate it into your script. Subsequently, the executable is launched on the computational resources allocated for the job. The duration of the parallel computing is logged using similar script variables, and you can choose whether to include this in your script. The remainder of the job script is as reviewed in video 29. We use the sbatch command to submit the job script to the Slurm queue system. We can track this job employing the sq command. The job has the specified name and has been active for 2 seconds on the B3366 node. Using the command again confirms that the job has finished. The job script creates a Slurm output file, but let's clear the terminal first. We can confirm this by using the ll command, which indicates that the file ending with txt has been created. Note that in your job script, we have renamed the Slurm output file to OpenMP on Betzy N32768. You can also observe that copies of both the job script and the Fortran program have been created. It's a good practice to save these files along with the Slurm output file to document the versions of the Fortran program and job script used for this job execution. Let's open this Slurm output file using the Emacs editor, and remember to use the Tab key for autocomplete while typing these long file names. The compilation took approximately 7 seconds, and the parallel computing time for a matrix size of 32,768 was about 39 seconds using 128 CPU cores. The job was submitted from the work folder. The specified computational resources are listed, showing that a single node with a single task using 128 CPU cores was requested. The CPU billing section shows that the billing factor was 128, which matches the number of CPU cores on one node. It also indicates that 242 gigabytes of memory are available on a single node. The job consumed 1.7 CPU hours from the project account. The file shows that the job waited 13 seconds in the queue. Although the requested wall time was 30 minutes, the job had a wall time of 49 seconds. The computation was a single task on 128 CPU cores, with a CPU utilization of about 73%. The exit status was 0, indicating the job was successful. The low CPU efficiency occurred because only one core was used during compilation, leaving the other 127 cores idle until the compiled program was executed. A single node has 242 gigabytes of available memory, and the Slurm output file confirms that this amount was allocated. The reported memory usage is 25.6 gigabytes, which aligns with expectations for a matrix dimension of 32,768. We can verify the job efficiency with the cef command, which stands for Slurm efficiency. The cef command shows the same numbers as those in the Slurm output file. Let's clear the terminal. We can append the output from the cef command to the Slurm output file by using two greater than signs. Let's check the Slurm output file to see if the Ceph output was added. The file shows that the Ceph output was appended at the end, after the memory statistics. We can try with a larger matrix dimension, so let's open the Fortran program with the Emacs editor. Inside the Fortran program, we'll adjust the matrix dimension to 65,536. Let's also make some changes to the job script. In the job script, we'll update the job name and the name of the Slurm output file. The job script is submitted to the Slurm queue system using the sbatch command. By using the sq command, we can track this job. The job with the specified name has been computing for 26 seconds on the B2338 node. Using the sq command again shows the job has been active for 1 minute and 32 seconds. A subsequent sq command confirms that the job has completed. Let's clear the terminal. The generation of a Slurm output file can be verified using the ll command, which shows that a new file ending with txt has been created. Let's open this Slurm file using the Emacs editor, and remember to use the tab key for autocomplete while typing these long file names. The compilation time was approximately 13 seconds, and the execution time was nearly 248 seconds for a matrix dimension of 65,536. The CPU utilization was about 88%. The memory allocation is still 242 gigabytes, but the memory usage is now around 98 gigabytes. This is expected for a matrix size of 65,536, as we observed similar memory usage when using the big mem nodes on the Fram Linux cluster. Let's exit the Slurm output file and clear the terminal. The ceph command can be used to verify the data from the Slurm file, confirming that the memory usage is about 98 gigabytes. The ceph output can be appended to the Slurm file as before. To use the scripts and files from these videos as templates for your work, you may copy them from the Saga Linux cluster. First, move to the folder Cluster, Work, Support, Parallel, Computing, YouTube. Use the ls command to display its contents. You'll recognize many scripts and files from the videos, and you can copy any of these files to the home folder. In our next video, we will explain how to schedule jobs on the Betzy Linux cluster using the math kernel library, MKL. I am looking forward to the next video, wishing you all happy computing in the meantime.